allowed us to literally go back in time on Mars.
The first picture will cover an area of 176 miles.
Mariner 4 began transmitting back images.
The first photograph that a human being has ever seen from the surface of another planet.
On August 20th, 1975, the first Viking spaceship was launched.
You are seeing something that no other human has ever seen before.
Former seas and mountains.
Huge canyons.
That sense of wonderment and achievement and always working towards your goal.
We can do, and we will do.
And liftoff.
Mars is unavoidably special.
We've landed and we've scooped.
We've roved, we've orbited.
Together we did it, but the attitude was together we can do it.
The future is what you make out of it. You can make it real.
And here we are with Mars Perseverance, 51 years later, getting ready to do the first ever Mars return mission.
Eventually, we can bring those samples back to Earth and determine for the very first time, did life exist on Mars?
I'm DC Eagle of NASA's Jet Propulsion Laboratory in Southern California. We're here at the Kennedy Space Center to talk about NASA's next mission to the Red Planet, Mars 2020 and the Perseverance Rover. And we're going to be talking about the science and engineering that's going to make this mission a great mission. Here to talk about Mars 2020 we have today Lori Glaze, the Director of the Planetary Science Division at NASA headquarters in Washington. And across the country, we have with us Jennifer Trosper, the Deputy Project Manager for Mars 2020 at JPL. Also at JPL, we have Farah Alibay, and she's a Mobility Engineer for Mars 2020, and she's, of course, also at JPL. Now back here at the Kennedy Space Center Media Site, we have Ken Farley, who is the Project Scientist for Mars 2020, and he is from Caltech. Finally, we have Tanja Bosak, and she's a Mars 2020 scientist from MIT. So we're going to start things out with Lori Glaze. Lori?
Great. Thanks, DC. So, as DC says, I'm the Director for the Planetary Science Division at NASA. And the main goal of NASA's planetary program is to explore the solar system to help us answer important questions about how the planets formed and how they evolved. And of course, there's a lot of really special places to go throughout the solar system, but Mars has always held a special place in that exploration. If I could have the first graphic, please. Going back to the Mariner missions, the Mariner flybys, and the Viking landings, Mars has always held that special place up through even our current missions, the current series of orbiters and landers and rovers that are currently operating on the surface today, and of course leading up to Perseverance, which is about to launch. Some of the reasons why we've always found Mars to just be such a special place and so fascinating: for one, it's relatively accessible. It's relatively close in the solar system. We can get there. We can arrive in a matter of about 6 to 7 months. So that's relatively short on the planetary exploration timescale. But in addition, it also holds a lot of really unique scientific value, particularly for trying to understand planets with rocky surfaces and planets with atmospheres, helping us understand how they form and evolve and help us better understand our own history on Earth. Mars preserves on its surface some incredibly complex and diverse geology. On Earth, of course, our crust is constantly recycled, weathered and eroded, and so it's very hard to find places that have preserved that history from billions of years ago. And yet on Mars, we can find places where we see that full breadth of history preserved onto the surface, on the surface. It also, of course, is a planet with an atmosphere. It has a climate, just like Earth has a climate. And much like Earth, the climate on Mars has changed over time. And so by understanding when and how that climate has changed helped us better understand our own climate evolution on Earth. It's also a place where on the surface, since it's so old, it's preserved. We've also understood that in the last about 20 years, we've come to better understand that the surface of Mars was actually probably much warmer and wetter in the past with a denser atmosphere, and that perhaps several billion years ago, life could have possibly taken form on Mars as well, similar as it did on Earth. And by going back to Mars, we might be able to find evidence of when life could have taken place or could have taken hold on Mars. This is a study of astrobiology, of understanding the environments that could support life and understanding if and when life can actually come to be. And Mars 2020 Perseverance is in fact our first mission from NASA that's specifically designed to answer these astrobiology questions on Mars. And if I could have the next graphic, please. But everyone will tell you that this is an incredibly complex mission, but they didn't do it alone. All of those that worked on this mission are leaning on the legacy of all those rovers that have come before, from Sojourner to Spirit and Opportunity to Curiosity and now to Perseverance. We're building on that legacy of what's come before, but Perseverance is also laying the groundwork for what comes next. You're going to hear a lot today about the incredible science that Perseverance is going to do on the surface of Mars and about its main goal, which is to collect some samples to bring back to Earth in the future. And our next big mission, of course, is going to be Mars Sample Return, where we plan to execute the first ever round trip to Mars and execute the first ever launch from the surface of another planet. And that whole mission will be focused on trying to bring those samples, those very precious samples, back to Earth where we can analyze them here with our incredibly capable laboratories here on Earth. And all of this is also then leading towards potential human exploration in the coming decades. We've got specific technologies on the Perseverance rover that you'll hear about that are also going to be talking about, that will be demonstrating these core capabilities that we're going to need in order to support human exploration in those coming decades. And I wanted to just give a plug real quick for two more press conferences that will be held tomorrow afternoon for both the technologies and for Mars Sample Return, if you want to learn more about those two things as well. And so right now what I'd like to do is hand it over to Jennifer Trosper, who's actually worked on all 5 of the rovers that have successfully been delivered to Mars by NASA and JPL. Jennifer is the Deputy Project Scientist for Surface Operations. She's going to tell us a little bit more about the rovers themselves, the rover itself, and about what we're going to do once we get to Mars.
Thanks, Lori. Well, it's great to be here today, and I'm very excited to tell you about our new rover, Perseverance. But I have to look back and say, you know, as a farm girl growing up in Ohio, it took me a while to get the rover bug. Now, I've worked on all of these rovers, but I didn't work on robotics growing up. But in 1997, I had the opportunity to be part of the Mars Pathfinder team with the Sojourner rover. And ever since that day, when we landed on Mars, and I saw the fun and the excitement and I got the bug of exploration, and so now I've worked on every Mars rover. It's been a privilege not just to work on the rovers, but also to work with the great teams that build these rovers. And today I'm going to tell you about our next great rover, Perseverance. Now go ahead and show the first slide. The first slide shows our predecessor rovers. You see the small rover is Sojourner rover, the one I just talked about. And then we have Spirit and Opportunity, the mid-size go-kart rover. And then Curiosity, which is more like a small car. And now we have Perseverance. And as I look back over my career of working on these rovers, it's exciting to see how we just incrementally built up the capabilities of the engineering and the science to have this enormously capable rover today called Perseverance. I'm going to talk a little bit about what those capabilities are. I would say Perseverance is unique in that all of her capabilities are very much focused on her science mission. Now, her science mission is challenging. She needs to go explore, find, select, actually core and cache samples for future return to Earth. And so we've needed to add a lot of new things to Perseverance to make her able to do that. And we want her to do that in a location that is interesting enough to find samples that we want to bring back to Earth. And so that brought us to needing to add our first new technology. Our first new technology was terrain relative navigation. Now, We leveraged a lot of the Curiosity entry, descent, and landing system, but when Ken Farley and the science team decided that they wanted to land at Jezero Crater, we realized that the current Sky Crane landing system would not land us there safely enough. And so, you know, you can kind of think if it's more scientifically interesting, then it has more engineering hazards. So you can go here to my next graphic, which shows what terrain relative navigation is. The engineering team, you know, got on board to say, well, we need to make this landing site safe. And so we added what is essentially our astronaut that we take to Mars that steers us away from hazards, and we call it terrain relative navigation. We can't take an astronaut, so we load Mars orbital maps that we get from the orbiters that are marked with hazards, and then we use a camera to take pictures as we're descending onto Mars, and then we compare those, figure out where we are in the map, and then divert by firing engines to get away from the hazards so that we can land safely. So this new technology allows us to land in Jezero Crater, which is where the science team wants to go to do this investigation. Now, another interesting part of entry, descent, and landing. Now, entry, descent, and landing is always harrowing. It's hard, right? Mars is 100 million miles away. You start at 12,000 miles per hour at the top of the atmosphere. You have to get to 0 7 minutes later. And so it's a nail-biting thing. And we've added something to Perseverance, which is especially cool, so that we will get a front row seat. The vehicle actually has the ability to take selfies as it's going through the entry, descent, and landing process. Go ahead and show my next slide. This shows you where the cameras are that we have added to take pictures as we're descending onto the surface of Mars. We have parachute uplook cameras that will watch the parachute inflation. On the descent stage, we have some downlook cameras that will watch the rover go down on the Sky Crane. On the rover, we have uplook and downlook cameras. The uplook cameras watch the descent stage and we'll get the flyaway moment, which is awesome. And then the downlook cameras will watch the surface as we're placed on the ground on Mars. Very exciting. We also have a microphone on the rover, so we're listening to ourselves as we go through the atmosphere of Mars. We're listening to the pyro firings and the hardware being released. It's going to be one of the most exciting things that happens early in this mission, and I'm really looking forward to it. We'll record all that data, and then we'll send it back shortly after landing. Now, the next thing that's exciting about this rover, you know, entry, descent, and landing is always exciting, but it's only 7 minutes. And my personal favorite part of the mission is the surface mission, which for Perseverance is going to last for a Mars year, which is about 2 Earth years. And this Perseverance mission has to do the equivalent of about what Curiosity did, or 4 times what Curiosity did in the same amount of time. And so we've had to do a lot of things to make it smarter. And so go ahead and bring up my next slide. You can see that this is one of the things that we've done to make it smarter and have better sensing is we've added some cameras. You can see we have 23 cameras on the rover, and some of the new cameras we've added, we have new EE cams that are our navigation cameras that we use for autonomous driving. They're now color, they're twice the field of view, twice the resolution as the Curiosity cameras. We also have added better cameras to the front of the rover, the hazard cameras, which we use to actually place the arm very accurately. We even have a camera inside the rover that takes images of the samples before we seal them off. So we have lots of great sensors. And another thing that we do to make the rover smarter is we add a lot of software and computers. So if you can go on to my next graphic, I can show you a little bit about what makes the rover smart. The rover has about 13 different computing and processors. It has dozens of electronics boxes. I can't show you the software and the algorithms that make it smart, but this is the inside of the rover. The back of the rover is to the right, the front of the rover is to the left, and you can't even see the full sample caching system, which is another extraordinarily complex part of the rover. If you were to take all of the cables inside the rover, it would be about 3.5 miles long. So it's a very complicated vehicle. But we've made it smarter. The things that we've done to make it smarter, some of the new algorithms, I talked about terrain relative navigation. We've also added new auto navigation algorithms so that we can actually drive autonomously through more difficult terrains that have more rocks. We've added a capability for higher compression so that we can get more data down to the ground. We've added a capability so that after the rover drives, it can stop, check for hazards, and if there are no hazards, it can actually deploy the arm out and take some images and send those back to Earth so that we don't have to wait for the next day, and it speeds things up. We've also made some significant upgrades to our operations system. We have cloud-based tools that allow the science team to do collaboration around targeting and visualization, and we're much more efficient at simulating and validating those sequences because we have to send those to the rover every single day. And now, if you'll go ahead to my next slide, which is my final image, I love this image because it shows the rover folded up, ready to go, on its way to Mars. But it also shows the preeminent new capability that we've built on this rover, which is the sampling system. If you look at the front of the rover, you see the cage-like feature. That's the corer. That cores the samples from the surface of Mars. You'll also see the robotic arm. You can see the forearm and the upper arm that have the Mars 2020 and the Perseverance plates on them. You'll also be able to see the bit carousel, which is sort of in the center, the round thing. A couple other things to say about this image. The wheels are covered with anti-static wrap, and we do take that off before launch, so no worries there. And then you can see the rover's upside down in this picture. So you see the mast is actually stowed underneath the rover. You can see the American flag there at the bottom of the mast. Now, something that just kind of brings it home as far as how amazing this rover is the turret that's on the end of the robotic arm that includes the corer and also includes some other instruments. It weighs 80 pounds. And I think if you had told me back in 1997 when I was working on the Sojourner rover that in 20 years we'd be building a rover that had a robotic arm that could hold the weight of 3 Sojourner rovers in its hand, I might have been surprised. But here it is. It's the Perseverance rover. It's an amazing vehicle. And with that, I'm going to hand it off to Farah Alibay, who will talk more about the mobility system.
Thank you so much, Jennifer. Perseverance has some of the most ambitious science goals that we've ever attempted on the surface of Mars. Now, in order to achieve these, we need to travel long distances and over a variety of terrains. The enabling technology for this is the rover's mobility system. Now let's cue up my first video where you'll see the rover driving here in our clean room, and while you look at that, I can talk you through some of the specs the rover has. Perseverance is a rugged, all-terrain vehicle. It has a clearance of 2 feet, a wheel diameter of 21 inches. It can go over obstacles of up to 40 centimeters, that's just over a foot, and it can go up slopes of up to 30 degrees, so that's about a 57% grade. The rover has a top speed of 0.1 mile per hour, but most importantly, it can self-drive on Mars. Now remember, Mars doesn't have roads, it doesn't have maps, it doesn't have GPS, and yet Perseverance can self-drive for distances of up to 200 meters per day. In order to get there, in order to get to these specs, we've had to make some pretty significant upgrades from Perseverance's predecessor, which was Curiosity. The first upgrade that we made is to its wheels, and let's look at slide number 2 where you'll see the difference between the Curiosity and the Perseverance wheels. And we essentially went back to the drawing board here. You can see that the Perseverance tread pattern is much tighter, much closer together, and the treads are actually taller, which gives the wheels better traction. You can also see that the treads have a smooth sinusoidal pattern rather than the jagged pattern that Curiosity had. That gets rid of the hot spots that cause damage on the Curiosity wheels and gives us confidence with that, and along with the hundreds of hours of testing, obviously, that we've done here on Earth, that these wheels will survive the harsh Martian environment that they will be driving on. The biggest upgrade that we've made to the Perseverance rover, however, is its self-driving capability. Perseverance is able to self-drive 3 times faster than the Curiosity rover can, and that is mostly due to its ability to think while it drives. It's able to do what we call thinking while driving due to its additional computer, the Vision Compute Element, or the VCE. Now, the VCE was added to the rover in order to enable terrain relative navigation, which Jennifer talked about. But once we're on the surface, we no longer need our terrain relative navigation software, so we reuse that second brain in order to speed up our autonomous navigation. The Scarecrow rover. Scarecrow, which you saw on that last picture, is an Earth version of our rover that has a third of the mass. And essentially, Scarecrow has the same weight here on Earth as Perseverance will have on Mars, since Mars has a third of the gravity that Earth does. So here on Earth, we'll be putting Scarecrow through a variety of tests through our mazes, and what we'll be doing using those tests is fine-tuning our self-driving parameters so that in February of 2021, when we land on Mars, we'll be ready to hit the ground running and get along with that fantastic science that we have in store for the rover. And with that, let me hand you over to project scientist Ken Farley, who's going to talk to you about that science.
Thanks, Farah. As you've heard, the Mars 2020 mission has 3 major goals. The first is to seek the signs of life. The second is to collect and cache a suite of samples that a future mission could bring back to Earth. And the third is to test technologies that future explorers of Mars, either robotic or possibly even human, could take advantage of. If I could have the first graphic. I want to tell you a little bit more about the rover, and in particular about the science instruments. We have 7 entirely new instruments that we are flying with us, and I want to focus on just 2 of them because they illustrate a completely new kind of capability for a rover mission, and that is the pair of instruments that are on the robotic arm on the turret that Jennifer talked about. These 2 instruments are called Sherlock and Pixel, and what they do is they allow us to combine or co-register in a single postage stamp size area things that you could see with your eyes, like color and texture, but also chemistry and mineralogy. And this is a very powerful combination. It's never been done before on Mars. And it will allow us to understand how rocks formed, what their history has been since they formed, and in particular is one of the key ways that we will look for evidence of life, for what we call biosignatures. And in that regard, the Sherlock instrument is particularly important because it will allow us to not only detect organic matter, but to also map its distribution in this microscopic area. And this is, of course, organic matter is, of course, one of the key kinds of observations that one makes to identify past evidence of life. In addition to those 2 instruments, I want to expand on something that Jennifer mentioned, which is the sample caching system. And I want to talk about something which I find really, really cool. This is a sample tube. Now, Jennifer told you that the sampling and caching system consists of a drill mounted out on the robotic arm and a system that processes the samples inside the rover. Well, this is one of the really key elements of this whole thing. This is a tube into which each individual sample will be drilled. It is a very complicated device. We often liken it to a test tube, but I think you can see it's got a lot of features that go beyond that simple description. And I want to tell you about some of them. First, one of the key technologies that had to be developed for this is how to make it extraordinarily clean. This is amongst the cleanest things that have ever been built, certainly is the cleanest thing that has ever been flown, in the sense that the inside of these tubes, of which there are 43 on board the rover that look just like this, inside of this tube has no microbes and is extremely clean of organic matter. And that's necessary so that when the cousins of this tube come back to Earth, we can be certain that what's inside that tube actually came from Mars and didn't come from Earth. There's several other features I can point out here. It's got a serial number on it. This will be very important for when the fetch mission goes to pick up this tube. We'll know which one it is and we'll know where we collected it. That's obviously super important. And you see lots of indentations and holes in the tube. This is necessary so that the robotic system, both on Perseverance and on the follow-on missions, can manipulate the tube. And finally, you also notice that it is bright white. This is not paint. Paint would contaminate the sample with organic matter. Instead, this is aluminum oxide, which has been flame sprayed onto the surface. And this is necessary so that when we cache the tube onto the surface, put it down on the surface for the future mission to pick up, it doesn't get too hot in the sun. The white reflects the heat away. So this is really one of the great features that has been built into the rover. And we spent a fair bit of time talking about the hardware of this mission, but I also want to point out that this takes a very large team of people to run. There are engineers who are responsible for commanding the rover and for ensuring its health and safety. And there's also a very large science team which will guide the operations in the pursuit of the science goals. The science team has about 350 members. They come from all around the world, and they range from students all the way through senior scientists, and they represent an enormous diversity of scientific disciplines, from people who are nitty-gritty experts about what each instrument does and how it does it, through to geologists and geochemists, atmospheric scientists, astrobiologists, and this whole team has to work together. One of the key things that Jennifer mentioned is that we have a very ambitious mission planned, and we need to work very efficiently. And one of the reasons for this is that the team each and every day will receive data from the rover, and on a very short time frame, the team needs to interpret that data. What questions did it answer? What new questions did it raise? And where do we go now? And what observations do we make? We have just a few hours to do that before we have to hand it back to the engineers, who then beam instructions up to the rover to go and do that. So this is a very time-pressured activity, and it is really important that the team know how to function together. And unlike a piece of hardware where you can design how all the elements interact, a human team is really quite different. And one of the things that we've been working on over the last few years since this team got together is a kind of bonding. And if I could have the next video clip. One of the things that some of us on the team were fortunate enough to be able to do is to go out into the field in a remote part of Western Australia to look at rocks that contain the oldest undisputed evidence of life on Earth, very similar to the kinds of things that we hope we might find on Mars. And so this was really a great activity so that we could all come together and really grasp the ideas behind this mission. We are now about 3 days away from the launch, and we will arrive, Perseverance will arrive on Mars in February of 2021. That gives us about 7 months in which the science team will not be relaxing. Instead, the science team is working to develop a plan for how we will investigate our landing site. If I can have the final clip. One of the things we've been doing is developing a notional traverse of how the rover will move through its landing site. So in blue you see the landing ellipse, and in white you see the traverse that the rover may take. And this shows that we have wonderful data from the orbiters that have been around Mars to guide us in the selection of key targets to further our science goals, and also the way we can traverse the rover through various hazards. So we're very excited to continue to work on that and then actually start executing as soon as we get to Mars early next year. And with that, I will turn it over to Tanja Bosak, who is a science team member and also an expert at looking for biosignatures in ancient terrestrial rocks.
Thank you, Ken. As someone who spends a lot of time thinking what life was like on Earth or Mars 3 billion years ago or more, I think that Jezero crater is an amazing site to examine and sample. The process by which we arrived to this landing site, to choose it, was long. It started in 2014 with the first landing site workshop, which was open to the entire community. So anyone could come and suggest their favorite landing site, and there were discussions, extensive discussions that led to the narrowing down of the number down to 3 sites in 2018. And then in November 2018, Dr. Thomas Zurbuchen made the final choice of Jezero. And the choice is pretty obvious when you think about what we can see from space. That tells us a lot about Jezero as a previously habitable environment. So if I can have the first slide, here is a photograph taken from space of the Jezero crater. This crater occurs in very old terrain. The crater itself is probably 3.8 billion years old. This is an amazingly old environment. And what we can see from this, the crater itself is about 50 kilometers wide, And in this dashed area, we see a fan. You see this fan already in Ken's slides. We know what forms these kinds of fan-like deposits on Earth, and those are deltas. Deltas occur when rivers flow through terrains and bring sediments into standing bodies of water. So just by looking at this picture, we can tell that there was a standing body of water that was there long enough for these sediments to be deposited and form these geomorphic features. So great, there was a standing body of water some time ago. What did it look like? So if I can have the movie that follows, this is an artist's rendition of a flyover many billion years ago over the crater. So if you can play the movie, we see on the left, there is the inflow channel that kept filling this crater with water. The water level was rising to the point when the outflow channel formed to the right, and that lasted for some time, long enough to create a delta. Now, we know a lot about deltas on Earth, and part of what makes deltaic environments so attractive is that they sample sediments from the surrounding regions. These very old regions would have been very old on Mars. So by looking at the sediments there, we can learn about the surrounding regions on Mars. However, for biosignatures, it's even more exciting because deltas are great at preserving organic matter and other types of biosignatures. And what we also know already from just orbital spectroscopy, if I can have the next slide, please, there are diverse minerals present in the delta and within our landing ellipse and the projected rover trajectory. So here's a false color image. These are not the real colors on Mars, unfortunately. It is not so colorful. But what these different colors show are areas in which different types of minerals are concentrated. So within the delta, you can see some purples, you can see some greens. Some of this tells us that there are a lot of clay minerals that are known on Earth to preserve good biosignatures. The green areas in particular, you can see this green that really follows the rim of the crater, but in the areas where the waters of the lake, former lake, would have been lapping the shore. And that is great for biosignatures if some of these minerals are precipitated. So here's where the ions would have come in, and minerals with the inflowing water, and some of them may have been concentrated and perhaps even trapped some biosignatures. And good analogs on Earth, in fact, some of the oldest evidence for life on Earth comes from rocks that are of the same similar composition to these green rocks. They're called carbonates. And if I can have the next slide, some of these rocks look like what follows. They are layered, they're made of carbonate. And so what we are looking here, we are back on Earth. This is a 2.7 billion-year-old rock, a stromatolite from Western Australia, the area we saw in Ken's video. And what we know about these rocks is how to look for biosignatures. So a lot of these little features you see here, different crinkly layers, different little bumps, we know when microbes have to be involved in the precipitation of minerals to make shapes like that. So are there stromatolites on Mars? We don't know. What are these carbonates on Mars? We don't know, but we are very excited to start looking at them. We certainly have a great suite of instruments to do so, and we have many sets of trained eyes that will be ready to sample the best rocks possible to bring to Earth and start asking these questions about possibly early life on Mars. So with that, I will turn it over to DC.
Thank you very much, Tanja. Understand we have some questions from the media on the phone. So first question goes to Chelsea Good of Space.com. Chelsea?
Hi, thank you so much for taking my question. So, obviously a huge part of this mission, one of its main objectives, is to look for these biosignatures and evidence of this ancient life. I'm curious, in part, for people who are just like, oh, what does that mean? I think, obviously we know what biosignatures are, but what are you hoping to find, I guess, more concretely? We've seen organics on Mars, we've seen things of that nature, but I'm curious what specifically you're looking to see. And then, the second part to that question is, I'm curious how you think people will react if these findings, if these biosignatures do come to light and Perseverance is able to take us to the next level in the search for life.
Yeah, okay. So what are we looking for? What is a biosignature, and how are we going to look for it? Well, the first thing to understand is that what we are looking for is likely very primitive life. We are not looking for advanced life forms that might leave things like bones or fern fossils, something like that. We are looking, by analogy to what we find in the similar time on Earth, microbial life. And Tanja showed you an image of a very compelling example from Earth of what that looks like. It's produced where a layer of microbes lives at the interface between water and mud at the bottom of a body of water. So that's the kind of feature that we could see with our eyes. The example that she showed was macroscopic. It was quite large. And if you looked at it with a microscope, which we will be able to do with the instruments on the arm that I described, you can see that texture goes right down to the microscopic scale, and that we would see that there is organic matter in the terrestrial analogs that we would hope to see with the Sherlock instrument. So that's a really, that would be a very compelling example of a biosignature that we might hope to find.
And I'll just add a little bit towards the second half of that question, which is even beyond, just trying to reach just a little bit beyond what we hope to achieve with Perseverance. You've heard a lot about the incredible science that we hope to do at Mars in looking for biosignatures. But we also think there are other destinations within the solar system that could also be potential places where life may have started to take hold in the past, or may actually be present even today. The moons of Jupiter and Saturn, such as Europa, which is a moon of Jupiter, Titan and Enceladus, moons of Saturn, are also places where there potentially could be environments that might be conducive to life, other very interesting astrobiology targets. And so we're interested in continuing to explore all of these different environments, Mars and beyond, to continue our search for, are there other places in the solar system that might actually host life?
Great. Thank you, Lori. I understand the next question is from Marcia Dunn with AP. Marcia?
Yes, hello. I have a question for Jennifer Trosper, if I might. I hate to ask you to choose among your 5 rover children, but I'm wondering if Perseverance is your new favorite child. And also, what to you, you've worked with all 5 NASA rovers, what to you sets Perseverance apart the most from its predecessors? And you're free to use as many superlatives as you like. Thank you.
Okay, thank you. So I think I have to first say about the rovers the same thing I say about my 3 children. They're all my favorites. And I also have to be careful because I actually met my husband because of the Pathfinder rover, so I think I have to say that one's my favorite. But Perseverance is also my favorite, so I don't think I answered your question. But the thing that I really love about Perseverance, and I've had a different role, more of a visionary role on Perseverance than I had on previous rovers, so it is more, I think, a part of who I am and what I want rovers to be. And I see Perseverance as being transformative, right? And I think Matt talked about it this morning. We've been exploring, we started exploring Mars with the orbiters, and then we got to where we had landers, and now we are driving around, and now this is transforming us to bringing samples back and eventually getting humans there. So I think that's the thing that makes Perseverance stand out uniquely amongst all of these rovers.
Great. Thank you, Jennifer. Next up, Mary Liz Bender with Inverse. Mary?
Yeah, thank you so much for taking my question. I was just curious if you could talk about what happens right after launch. What do the next steps, the next couple months look like for you, the team? And when will you take your first real fresh sigh of relief, if you will?
Jennifer, that one might be for you.
And that could go to anyone, but Lori, perhaps you want to answer that question?
Oh. Sure. Well, I'll leave some of the details of exactly what's going to be happening over the next few months, maybe to Ken and to Jennifer. But when will we heave a sigh of relief? I think after we've successfully completed the entry, descent, and landing, and gotten through that 7 minutes of terror, I think all of us will be very relieved and ready to begin the hard work of conducting the surface science and starting to see the incredible results of the fruits of our labor here. But I'm gonna let Ken or Jennifer talk about what we're going to be doing over the next few months.
Well, I'll just say what the science team is going to be doing: training. It's a very complicated piece of hardware, and the scientists on this mission, most of them have very little preparation to do this kind of work. We have to understand what the instruments are capable of and how to instruct them to do what we want them to do. So training is really essential at this point.
Jennifer, anything to add from JPL?
Yeah, I'll add that we have a cruise team that is actually flying the vehicle to Mars. So shortly after launch, we'll actually be able to see the sun on our solar arrays and our sun sensors. We'll be able to find the stars in the sky with our star scanner, and we'll get our attitude initialized. We'll get to the right spin rate. And then within a few weeks, we'll do our first trajectory correction maneuver, which essentially just gets us on the home and transfer trajectory that we're taking to Mars and corrects for any launch vehicle errors.
Great. Thank you very much, Jennifer. Next up from Irish Television, Leo Enright. Leo?
Thanks very much, DC. For Ken Farley, I rather loved the dotted lines on the traverse map that you showed. Could you talk a little bit about the extended mission? I mean, we're all hoping you'd go beyond Midway, but it looks like at the moment you're only prepared to go as far as Midway, or am I reading that map right?
Yeah, let me provide some background here. During the landing site selection process, the community that was doing the prioritization recognized that Jezero Crater had some really fantastic targets, and Tanja talked about them, the delta, the carbonate rock, very excited to see those. But there was also a great deal of excitement to rove up the crater rim and explore the highlands beyond, which is includes some of the oldest rocks on Mars, some very unusual features that could potentially indicate the interaction of hot water with rock, another habitable environment that we would be very excited to investigate. But it's important to recognize that we have a prime mission that, as Jennifer mentioned, is 1 Mars year, and so that traverse indicates where we hope to get by the end of the prime mission, about 2 Earth years after we land.
Great. Okay. Next up is Natalie Guerrero. Natalie?
Yeah, I wanted to know, what is the process for choosing what samples you end up taking, because it sounds like there's a limited number of sample tubes.
I can take that one. We have 43 sample tubes, and we expect that over the entire duration of the mission, not within the prime mission, that we will use all of these tubes in the pursuit of something like 30 or 35 really good samples. The additional tubes are there so that we can, for example, change our minds. We might say, oh, this looks like a good example of some particular kind of rock, and then 6 months later we find something that's much better. So we have an ability to kind of change our mind in thinking about what samples come back. It's important to understand that one of the central goals of the mission is to seek the signs of life. And many of the samples that we collect will be specifically chosen because they represent habitable environments, or if we are fortunate, also have potential biosignatures in them that we wish to investigate further. But there are also many other kinds of questions. We heard earlier about how Mars climate changed. It changed enormously. And an important thing to understand is that we have no idea why Mars was so different in its early history. And we hope that if we bring back rocks and study them in terrestrial laboratories, they'll tell us something about that. So I guess the idea is that we have a broad set of scientific objectives that we believe the samples can and will be used for. And the key really is diversity. We will collect a diversity of samples. This reflects not only our understanding of what questions are likely to be answered, but also recognizing that decades from now, there will be many other kinds of questions that we can't presently foresee. So having a diverse sample suite is the best way to approach that collection of the cache.
Great. Thank you, Ken. And we have some questions from social media. The first one is from Tor, and he is in the UK. And he's been building his own Lego and Kinects rover for a month and waiting for the launch of Mars 2020. So he would like to know, and perhaps Tanja, this might be a good one for you, how can you fit an entire science laboratory into a rover?
So part of what makes this particular rover so special is that we don't have to fit an entire science laboratory in this rover. For example, as Ken mentioned, the biosignatures we can look for will probably be something microscopic. And there is just no way to bring a microscope, a real microscope that we would use on Earth, to the surface of Mars. So this special rover and its special sampling and caching equipment is designed to store the samples, and eventually these samples will come to Earth, and then we can study them in laboratories on Earth. That said, there's a suite of instruments, that Ken mentioned. So there's Watson, there's Sherlock, there are all these instruments that can allow us to look at some rock textures and look for some organic material. So we can know a lot even just by looking at rocks on Mars.
Thank you, Tanja. Next question, this might be a good one for Farah. Farah, since you're about mobility, this is a question about keeping camera lenses clear of debris and dirt. How do you do that with the nav cameras that are going to be supporting the drives?
So on landing, the cameras are covered with camera covers, which protects the cameras from that dust. So we've tried to keep the cameras as clean as we can right now, and then after the landing sequence, we'll fire some pyros to get rid of those camera covers, and that should give us really clear vision on Mars. Other than that, typically we don't tend to get too much sand accumulating on the cameras that are up on the turret, so we don't worry too much about that. And we also benefit sometimes from the winds that serve as cleaning events for any dust that might get up there.
Great. Thank you, Farah. The next question is from Brittany Wright. And Brittany Wright writes, I'd love to know what the expected lifespan of Perseverance is and how you go about making repairs to it if anything should break or malfunction. Maybe that's a good one for Jennifer.
Yeah, we have tested and qualified our hardware to 1.5 Mars years, so that's longer than the 1 Mars year or the 2 Earth years that the mission is supposed to last. The way that we do that, we actually take it through all the thermal cycles. The thermal cycles on Mars are the hardest parts about the hardware that could break the hardware, and so we do that and we make sure that it will last through all those thermal cycles, and we make sure that our mechanisms will move as many revs as we need them to. So we've done that. We expect this to last 1 Mars year. Now the question about what do we do if things go wrong is an interesting one, because having operated all of these Mars rovers, there's all kinds of things that just go wrong, and it's far away, and sometimes it doesn't talk to you, and that's the first problem you notice. So there are a lot of different methods, and a lot of them are in our design, really. And I'll just talk to a couple of them. The first one is that we have redundancy in our critical hardware. So if the flight computer goes bad, we have another flight computer that can replace it. We also have something called functional redundancy, where we have, for example, we can talk directly to the rover from Earth via uplink and sending it commands, but we can also send those commands through orbiters if for some reason we lose the link to the rover from direct to Earth. So we have those types of things. It's always harrowing when you don't hear from the rover. Some great stories about getting these rovers out of difficult situations, but the team of operations personnel are very well experienced and suited to help the rover whenever it has some problems.
Great. Thank you, Jennifer. And actually, one more question for you, and this one's from Michael Jackal. And he writes, what is the hardest part about building the rover?
Well, Perseverance is a very complicated rover. I think I showed you different pieces of it during my presentation. The hardest part of this rover, there are many parts that are hard, but the sampling and caching system is a robotically complex system. You have to hand samples back and forth between different robot arms through a bit carousel. And then on top of that, it has to be super clean so that whatever you discover is not something that you took with you because it wasn't clean enough when you launched it. So that has been the hardest thing to develop on the Perseverance rover. And it's really, I think, a real testament that the team has been able to get that to the point where we can collect these samples and launch in the 2020 launch window.
Great. Thank you, Jennifer. Well, we're coming up at the top of the hour soon, so it's probably a good time to wrap the show. A reminder that tomorrow we have 2 more briefings about the Mars 2020 Perseverance rover mission. The first one's at 2 p.m. Eastern, and that's on sample return. That should be a real good one. And then 2 hours later at 4 p.m. Eastern, we have one on Mars 2020 mission tech and humans to Mars. So those are 2 good media briefings tomorrow. A reminder, of course, that July 30th is the opening of our launch period, and commentary will start on July 30th at 7 a.m. and 7:50 a.m. is the first opportunity for launch that day. Don't forget to follow the mission on social media at NASA Persevere on Twitter and Facebook, and please feel free to join the conversation using the hashtag #CountdownToMars. So that's it from here at KSC Press Site. I'm DC Agel. You guys have a good evening. Thank you.